that we did together with Mike and Benjamin. And the driving question behind this line of research was whether it's a good idea to combine property-based testing in the style of QuickCheck with fuzzing in the style of AFL. And spoiler alert, since I'm here, the answer is yes. But before I actually tell you why, let me give you a brief overview, a brief introduction to the two different techniques I described there. So welcome to Fuzzing 101. We start with a binary executable, and we feed it some number of random binary inputs. Then we generate more and more binary inputs in hopes that one of these inputs will lead to a crash. The devil, of course, is in the details, and the details in this case is how we generate these inputs. So let's look at different flavors of fuzzing and how they compare together. Here in this graph, I have plotted an x-axis that's bug finding efficiency, how good different techniques are at finding bugs. And on the y-axis, we have user effort, how much effort the user had to spend in order to actually generate these inputs. The ideal would be, of course, to be on the bottom right, where with no user effort, all bugs are found fast. On the bottom left, we have completely random fuzzing. We generate those binary inputs completely at random. That takes no user effort, but at the same time doesn't really find all the bugs. At the other extreme, we have, at the top left, we have fuzzing with custom input generators. You can write your own grammar, generate mutations based on that grammar, and the more effort you put into it, the better your bug finding efficiency will be. But again, you have to spend all that effort in order to get there. And there are tons and tons of work there in the middle. Rohan, right after, will talk to us about an approach to reduce the user effort in domain-specific techniques. But what I'm actually going to focus on today is coverage-guided fuzzing in the style of AFL. So let's take a deeper look. We start in coverage-guided fuzzing with some initial seeds, and we execute the program under test. If at any point during this entire process we find a crash, we report to the user, but more often than not, that will not be the case. If we don't find a crash, we check to see if that input is interesting. What do I mean by interesting? We instrument the program with extracting coverage information, and we check whether this binary input led to new paths in the execution being explored. If it is, we add it to the seed pool. Then we pick one of those binary inputs from the seed pool based on some search strategy and mutate it a bit to generate a nearby binary input, and then repeat this process all over until we are satisfied. Congratulations, you graduated from Fuzzing 101. So let's go to property-based testing. Property-based testing, as popularized by Haskell's QuickCheck, requires the users to write a formal specification. They have to write a set of properties that characterize the behavior of a system. In my talk, my examples are not going to be in Haskell, they're going to be in Coq, and I'm going to be using QuickCheck, which is a property-based testing tool for Coq. Started out as a port of Haskell's QuickCheck, but I've been feeding it steroids ever since. So here, to make things concrete, is an example property in Coq. It's a very simple property that states that for all lists of natural numbers, if you sort the list, the result is sorted. How do we test such a thing in property-based testing? Well, we generate structured type data. We generate lists of natural numbers, execute this property many, many times, and hopefully we'll find a counterexample. We'll find an input for which this property returns false. So one key observation here is that while traditionally fuzz testing and property-based testing communities were different and don't really talk to each other, they're really not that much different. In fact, you can view fuzzing as the special case of property-based testing. What's the property? For all binary inputs, running the program doesn't lead to a crash. Of course, the fact that we have specialized the property in fuzz testing in such an aggressive way allows us to do a lot more optimization and specialized techniques in order to make generation fast and make testing efficient. But let's keep this observation in mind and continue. Fuzz testing, the random property-based testing workflow is much simpler than the fuzzing one. You start with a generator that takes some sort of randomness and converts it to random structured data. Think random lists of natural numbers. And then we execute the system under testing the property. If at any point that fails, we report to the user. Otherwise, we keep going again and again, repeatedly sampling the generator and getting independent inputs. Okay? That works in a lot of cases, but not always. Here's a classical example of a property that doesn't really work well, which is a property that has a precondition. This property states that for all natural numbers x and for all lists of natural numbers, if that list is sorted, then we can insert x into the list and preserve this sortedness, right? The default behavior for Quick Check and most property-based testing tools will be that we generate random lists, test if the precondition there, if the list is sorted, and if it's not sorted, we're just going to throw it away because the entire property is vacuously holds. It's satisfied trivially. So the interesting part of the property, the insertion, is only going to be tested if the precondition is satisfied. And now, as we go to harder and harder preconditions to satisfy, this is not going to lead to efficient testing, right? So there is a solution to this, and in the property-based testing world, the solution is to write a generator that produces such lists directly, to write a generator for inputs that satisfy the precondition. In this case, it's relatively straightforward. We can just generate an arbitrary list and then sort it. But it's not always that easy. So let's put things into perspective. I have the same exact graph of user effort versus bug finding efficiency, only in this case, I'm only talking about the user effort for generation, not about any effort in actually coming up with the property that you care about. That's a different story. On the bottom left, we have naive random testing, this generate and test approach that generates random lists and hopes that they're sorted. No user effort, but also not really effective. On the top right, we have handwritten generators. We can write complicated programs that generate inputs with whatever distribution you want. And this can lead to amazing results. Consider, for example, Sysmith. It uncovered bugs, hundreds of bugs in GCC or LLVM, and it was a research contribution, right? It was a paper in its own right. So what's there in the middle? And because property-based testing and fuzzing are so similar, because we can view fuzz testing as an instance of property-based testing, the key insight of our work, and if you take anything out of this talk, this is what you should get, is that just like you can use coverage-based testing, coverage information to guide the mutation of binary inputs in AFL style, you can use coverage information to mutate structured data that are inputs for property-based testing in exactly the same way. Which brings us to coverage-guided property-based testing. In this workflow chart, I just took the other two and smooshed them together. So just like in random testing, we start with a generator that produces random structured data. We execute the system under test. If at any point throughout this process we find a counterexample, we report to the user and we're happy. If we don't find a counterexample, we now have instrumentation that gives us coverage information and allow us to check if that input was interesting, if it uncovered new paths during our execution. If it did, we add it to a seed pool. And here, the seed pool is not a set or a collection of binary data. It's now structured data. It's lists, it's terms, it's C programs, whatever you're testing. Now we pick one of those structured data, and we have to mutate it. We have to find a way of generating data that are nearby, just like we do in fuzz testing. Now, how does this differ? There are three fundamental differences that don't really appear in any of the other two techniques when you view them solo. The first one is the semantic mutator. This is something new that we have to work on generating structure mutations that take care and respect the typing relation. And that's what I'm going to focus on next. But there are two more things. The first is that we actually have a bit more information. Whenever we execute a property with a structured data, we now know whether it satisfies the precondition we're interested in. And it makes a big difference if we fuzz and give priority to mutating inputs that satisfy the precondition. If you've generated some well-typed program, it's much more interesting to try and find other well-typed programs next to it rather than starting from scratch and trying to find well-typed programs again. And that's also a conclusion that Zest found earlier this year. The third point is the fact that we can actually choose whether we're going to generate or semantically mutate at any given point, right? So we can start off by using the generator to produce seeds for fuzzing. Then we can use fuzzing to explore areas around those generators. And then if at any point we're stuck and we find that fuzzing can no longer uncover new paths, we can go back to generating randomly and starting to reseed the whole process. But I don't have time to talk about everything, so I'll just talk a bit about these semantic mutators. So what are these mutators? They are basically generators that take a parameter, and the parameter is the input seed that you want to mutate. So we take some high-level data structure. For example, here we have a tree, and we want to produce a distribution of all stepwise variants that are somehow one step away from the original one. And all of our semantic mutators are inspired by their equivalents in fuzz testing. So one kind of mutation that happens at the binary level by AFL is that it modifies bits. It flips bits, it flips sequences of bits together. When you try to find its analog when you're mutating higher level data, that corresponds to modifying components of your structure. For example, you could change that 1 to a 0 or that 4 to a 5. A second class of mutations that AFL performs results in deleting bits. So you could delete a bunch of bits together or something like that. You can't really do the same thing by deleting bits in the underlying representation of a data type, right? If I have a bit representation of a data type, you don't want to just randomly delete bits, because that's going to get you nowhere. But you can just delete subcomponents or subterms of whatever input you had. So for example, starting from that tree, we can delete the left subtree or the right subtree or whatever combination of those you want. Finally, another general class of mutations in fuzz testing results in adding new bits. And that could be by duplicating bits that you have or by splicing other interesting seeds into your seeds. But here we can go a step further. Because we have access to generators, we have access to the full power of a property-based testing framework, we can do those things by duplicating nodes, or we can just come up with new nodes and new things out of thin air. But we also have to be careful, because we don't really want to stray too far from the original input. We don't want to go too far and invalidate what made it interesting. Great. So that gives you a general idea of what our FuzzJig does, but how does it work? And our case study was on evaluating noninterference. In this case, we start with some set of abstract machines. Our abstract machines are very simple. They have a register file, they have a heap, all of those are just integers, and we have some sort of instruction memory that's conveniently independent from the heap. Now, in information flow control, we attach security labels to every single piece of data in our machine. So we say that each piece of data is either public or secret, and the goal is that secret data somehow does not affect public ones. How do we enforce that? Well, to enforce that, we start with two machines. It's what's called a hyperproperty. So we start with two machines that are almost identical. They're indistinguishable, which means that they are allowed to differ only on data which are tagged secret, right? So if we change that one which is tagged secret in the register file to 0, these machines stay indistinguishable even though they're otherwise identical. Now, the idea behind noninterference, which is the property we care about in information flow control, is that if you start with these indistinguishable machines that only differ in high data and you let them run for a bit, then you stay indistinguishable. So someone that doesn't have access to the secret data cannot observe any changes into the public locations of the machines eventually. In terms of a quick check property, that gives rise to this thing. We start with two machines, M1 and M2, that are indistinguishable, and we let them both take a step. Those should still remain indistinguishable. And this is a perfect example of a property that has a sparse precondition, right? If you remember what we were talking about in the beginning, this precondition, indistinguishability, is very, very hard to satisfy randomly. If you generate two random machines, they're almost guaranteed to not be indistinguishable. So what we want to compare against is we have three approaches that we want to test. This very naive generate and test approach that we expect to be horrible. The original case study on testing noninterference, which was the point of an ICFP paper 6 years ago that brought us, that has optimized generators for testing these sorts of machines, and an approach with FuzzJig with automatically derived generators and mutators. Now, that case study also had a very convenient benchmark suite that we could reuse. And here on the x-axis, you can see 33 different bugs that were systematically injected and aimed to cover all different violations of non-interference for that machine. So we have 33 different bars, and the y-axis is the mean time to failure in log scale. Mean time to failure, I mean the average time to find each bug with the 3 different methods, and that is basically the ultimate metric for what we care about, how good each approach is at finding bugs. So what are the results? At the bottom with blue, you have handwritten generators. They were extremely well optimized and find most bugs within a second. Also, it was an ICFP paper. At the very top, we have the purely random generators, the ones that QuickCheck derives and tries to produce indistinguishable machines using generate and test. Those are, as one might expect, extremely bad. Within a time limit of 4 hours, they find almost no bugs at all, except for the 2 simplest ones. Now, FuzzCheck lies conveniently in the middle. We find most bugs within a couple of minutes, so it's still relatively practical for debugging your machine. However, it doesn't find all of the bugs, and it's 2 to 3 orders of magnitude slower than the optimized handwritten generators. So in general, we find that FuzzCheck has a lot of promise because it actually bridges the gap between the two, but there's also a lot of room for improvement. Now there's one tiny detail that I haven't talked about, which is I talked that we had almost automatic generators, and that is this part, is what generator are we using to generate the indistinguishable machines for FuzzCheck. And there are basically 2 approaches here. Generate 2 random states, mutate them until they become low indistinguishable, and test them, or generate 1 random state, copy it, and then mutate until they become interesting. The graph that I showed you previously is using generator number 2, but generator number 1 is not that much different, and in any case, both of these are not more than 1 line of code. How much time do I have? I'm running out of time. So there's a very, very, very interesting piece of related work. It's called Crowbar. The idea is that they also try to combine property-based testing and fuzzing. And what they fuzz there is the source of randomness for this generator. So you view generators as a program that takes a binary input from dev random or something and converts it to structured data, and you fuzz that. You fuzz that binary input. It works very well for different applications, but I don't really have time to talk about it more right now. If you want, come find me after. So let's conclude. I showed you FuzzCheck as an approach that lies solidly in the middle, somewhere between handwritten generators and naive random testing. But in my mind, FuzzCheck is not really one point in this area. FuzzCheck is an approach that captures an entire space in this area because there are a lot of parameters to tune. There is a lot of configuration to be made. For example, standard concerns in fuzzing, like the search strategy, how you pick the next thing to mutate, or the power schedule, how much you mutate each seed, are still valid. And we have even more concerns that are somehow new. How do we combine generation and mutator? When do we pick to generate each one? How do we take discard information into account, like zest? What should the distribution of the mutators be? Because I showed you what the mutators are, but how do you combine them? How do you pick which one to apply? All of these are very interesting questions, and we just made an educated choice for each one that we thought was valid, but we don't really know yet how each one of these affects the overall performance. We haven't compared these carefully. Moreover, there are more ideas we can borrow from the fuzzing community, right? Fuzzing has created a ton of techniques, for example, using smarter coverage-guided fuzzing methods with concolic execution or symbolic techniques, and all of those should have corresponding counterparts to property-based testing. So to summarize, I introduced coverage-guided property-based testing and implemented it in FuzzCheck. We evaluated FuzzCheck in a security application and found that while FuzzCheck significantly outperforms QuickCheck and standard property-based testing tools, it requires a lot of, it still has a long way to go until we reach the performance of handwritten generators. And with a shameless plug that I'm on the job market right now, I'll take your questions. Thank you.
you. We have time for a couple of questions.
So, in your evaluation, then you looked at how well Fuzztrick would perform if you started off with a completely naive generator, right?
Yeah.
But what if you had taken those handwritten generators that we know are already pretty good and used Fuzztrick with them? Might you have worked even better?
So, no. The answer is actually no. The overhead of instrumentation in that case makes it worse because those generators are about as good as you can make them. So you're getting no benefit out of the fuzzing. But those generators are not automatically derived to generate indistinguishable machines. There's a whole line of work on deriving generators for constrained data that are still an order of magnitude worse than the handwritten ones. So I expect Fuzztrick would be a perfect complement to those, so that you can bridge the gap between other automatic techniques and fuzzing. Yeah.
So it wasn't clear whether these handwritten generators are those with how it's called? My mind stopped. With the technique that you had for
In Popple?
Yeah, in the ICFP paper, there was this by simulation or not? No,
the generation by execution.
By execution.
Yeah,
yes.
yeah, yeah. It's the generators in that we're using generators by execution, optimized further because there's been 5 more years of looking at this case study, and adapted for a much more complicated machine.
And how is the path coverage fed back to the generators here?
Yes. So all these generators are written in Coq, and that is extracted to OCaml. And the Crowbar people actually instrumented the OCaml compiler to get AFL to fuzz that. So I just reused all their effort at instrumenting the AFL compiler, the OCaml compiler, and I just use all that instrumentation in the same way that AFL uses it. So to keep comparison as fair as possible with the fuzzing tools, I just had the exact same search strategy that AFL uses, the exact same power schedule. All of those things are exactly the same to avoid configuration and being able to draw reasonable conclusions. And all the engineering effort was done by someone else.